Hi students. So in this video we will see how to find the transfer function of a system if the magnitude plot of the Bode plot is given. So it is just exactly reversely finding the transfer function, that is the open loop transfer function of a system if we have been given the magnitude plot of the Bode plot. So let us start with the analysis. Okay, now assume that this is the magnitude plot of a particular system. We are supposed to find the open loop transfer function of this system, which is GFS into HFS in time constant form. So this is, I want to find it in time constant form. Of course, we know that we can able to represent GFS into HFS, that is the transfer function, in two different forms. So okay, let me just talk about if the transfer function is represented in the form of something like, okay, 10 by s plus 2 and s plus 5. So then we will call this as the pole zero form representation of a given transfer function. Then how do we find the time constant form representation of the same transfer function? So in time constant form, we know that we want to get the transfer function in the form of 1 plus s tau. So now this 10 is there, I'll take out 2 from this factor. Now this will become s by 2 plus 1. I will take out 5 as common factor. This will become s by 5 plus 1. Now I can write it as 10 by 10. Can I write it as 1 plus 0.5s and 1 plus 0.2s. Now ultimately this will go off. So you have a transfer function which is 1 over 1 plus 0.5s and 1 plus 0.2s. So these two are similar transfer function, or not just similar, they are same transfer functions, but this is represented in pole zero form, this is represented in time constant form. The representation of this is called as time constant form representation of the same transfer function. So in this case we represent the poles and zeros in the form of 1 plus s tau. So this is 1 plus s tau, where tau is the time constant. We can exactly know the cutoff frequency of this, which is nothing but 1 over tau. So 1 over tau is 1 over 0.5, which happens to be 2. 1 over 0.2 happens to be 5. So we exactly get the same transfer function in pole zero form from the time constant form. If I take 0.5 outside and 0.2 outside, I'll get back the same transfer function. Fine. So keeping this in mind, because for this particular video I have to know these many things. Okay, let me just put it back here. And we are looking at transfer functions in pole zero form and time constant form. So I should be knowing what is root locus gain and system gain. So let us talk about what is this root locus gain and system gain. So in this transfer function, we had this in pole zero form. Whatever gain you have, this I'll call it as root locus gain. This will call it as root locus gain of the system. The gain whatever I'm going to represent, the k value what I'm going to get in the time constant form is called as system gain. This is system gain. For this system, 10 is the root locus gain, 1 is the system gain. So both are same transfer function. This value of k what I'm having is called as root locus gain because the representation is in pole zero form. Here the representation is in time constant form. The corresponding k is now system gain. Fine. So now let us now write the transfer function of a given Bode plot in time constant form. So let us try to identify what is the initial slope. So since the initial slope is minus 20 dB per decade, we know that there is a pole at the origin. So I have a term 1 over s. So let me write it as k by s. Now there is a constant value. We don't know what is the origin magnitude, origin frequency also. but let us write it as k by s is the representation of this minus 20 dB per decade line, and then you can see the slope becomes 0 dB per decade after 0.4. Now where is now, so this is my time constant. So how do I write this as now? So this 0.5 was actually time constant. So how do I write the frequency of this? So frequency of this is actually, so now if I want to write, now there is a change in the slope. Actually slope is increasing. If there is an increase in the slope, it means that it is due to a 0. It is due to a 0. So I will write it as 1 plus s by cutoff frequency is 0.4. So because this is frequency, so you have to write frequency, because we know that frequency is 1 over I want to write this tau. So how do you write tau? So tau is nothing but 1 over the frequency. What the frequency it is? 0.4. So that's why I'm writing it as s by 0.4. So now then what is this now? So if you see here, at frequency of 10 radian per second, is the slope becoming minus 20 dB per decade, meaning that there is a pole, because the slope was initially minus 20 dB per decade, the slope has become 0. It is due to addition of a 0 at 0.4 radian per second. Now at 10 slope is reducing, meaning that there is a pole at 10 radian per second. So I will write 1 by s by 10. Then you can see there is one more change in slope happening at 50. Since the slope is further reducing from minus 20 to minus 40, there is one more pole at 50. So I will write it as 1 plus s by 50. Now we are done with all the poles and zeros of this system. Now we need to find out what is the value of k. So to know the value of k, we know that at 0.4 radian per second, we have been given the magnitude as 60 dB. So at 0.4 radian per second, at this frequency, which all terms of this are contributing to the magnitude plot? Because we know that the contribution of this is there throughout the plot. The contribution of this s is also there throughout the plot, whereas the contribution of this will start from after 0.4. So after 0.4 only its contribution starts, and the contribution of this will start from 10. The contribution of this term will start from 50 radian per second. So at 0.4 radian per second, we have only these two terms contributing to the magnitude. Only these two terms contributing to magnitude, and the magnitude is 60 dB. So what I'll do now is, in terms of dBs, 60 dB is equal to 20 log of k, 20 log of k minus of 20 log of omega. Now omega is equal to 0.4. So at 0.4 radian per second, these two terms will contribute, and its magnitude is 60 dB. So since we know the value of, so in this equation, everything we know except the value of k. So now you make it 60 is equal to 20 log k minus 20 log 0.4. You can just simply feed this equation and get the value directly the value of k immediately. So what I'll do is, I'll just edit this equation, enter this equation. It is 60 alpha equals 20 log alpha a minus 20 log 0.4. So now I'll do shift cal. I'll get the value of k directly. Here. Now you can see the value of k is coming out to be 400. No need to simplify anything. So if you feed this equation, directly you'll get it. To verify whether you get it as 400 or not, so what I'll do is, so I'll go back to this equation, I'll take out this 60 dB. So now 20 log A is there, minus 20 log 0.4 is there. 0.4 is there. I will calculate for a value of that k is equal to 400. Can you see it is now 60 dB? Meaning 20 log of 400 minus 20 log of 0.4. Can you see now it is 60 dB? So this way you can directly feed this equation to your calc and then get the value of k immediately. So no need to just put this onto left hand side and put these things on right hand side and then or do all those stuff. So feed the equation as it is, you will get the value of k as 400. So we are done with k as 400. And one more term that they have asked is what is the value of omega GC, that is gain crossover frequency. So we need to find now assume that this is 0 dB. Not assume, this is 0 dB. So since it is 0 dB, it is the magnitude is crossing, magnitude plot is crossing 0 dB. Now this happens to be omega GC. To find this omega GC, at this omega GC, what all terms are contributing? Since before this, all the terms are contributing, I have to consider all the terms and equate it to 0 and find that omega GC. Find that omega that corresponds to omega GC. I will make it 0 equals 20 log k, we already know it as 400, minus 20 log omega, that's what is this, and then minus, so shall I write it as 20, sorry, this is for this 20 log under root of 1 plus, so what is 1 over 0.4? I think 0.4 inverse is 2.5. So shall I write it as 2.5 omega whole square as the term, and how about this term? Minus 20 log of under root of 1 square plus, so omega by 10 is 0.1 omega whole square, and one more term is minus 20 log under root of 1 plus, so 50 is, I think it's 0.02, 51 over is 0.02 omega whole square. See, carefully observe this. We have the equation. I am just writing the terms corresponding to all the terms. So this is 20 log 400 and this is minus 20 log omega. So there is a 0 at 0.4. Its time constant will be 2.5 omega whole square, and this 10 is the frequency, its time constant is 0.1, so and so. Now if I solve for this, I will get, because I have equated this to 0, I will get omega GC. I'll get omega GC. But since this is an asymptotic plot, whatever frequency, whatever omega GC you will get will not tally with on your semi-log sheet. Because on the semi-log sheet we will plot an asymptotic plot. It's an approximate plot. So to get the exact value what you get in your the semi-log sheet, we have to make a slight adjustment. So let me not take this one into consideration while calculating the omega GC. So if I don't consider this one, then whatever frequency I'll get will be 100% matching with your asymptotic value which is in the graph. If you consider 1, it will be the absolute value. If you don't consider 1, then it will be the asymptotic value. So since we want to find the asymptotic value, so let us remove this one. Let's just neglect this one and then take this. So whenever I actually do this 20 log of under root of 2.5 omega square, can you see this and this will go off, this and this will go off, and this square root and this square will go off. Now my life will become easy. I will simply equate. Now you can see what I'll do is I'll equate 0 alpha equals 20 log 400 minus 20 log alpha a, because this is the parameter what you are supposed to find. So 20 log a plus 20 log of 2.5 alpha a, close the parenthesis, because that square and this square root will go off, so it is only this much, so it is plus 20 log so and so, and now it is minus 20 log of, what do you have, 0.1 alpha a minus 20 log of 0.02 alpha a, close. Now we have entered all the parameters, we have equated that to 0 also, Now I will do shift cal. Now whatever value I will get will be omega gc. So naturally you can see omega gc will be away from 50, it will be more than 50. Can you see it is now 707 radian per second. So this omega gc is 707 radian per second. So what I'll do is, what I'll ask you is, you similarly plot this on a semilog sheet, you'll exactly get the same thing. So now omega gc happens to be 707 radian per second. Let me explain this again. I think there is no issue in writing these terms. So initially you start with k. Since we have an initial slope of minus 20, it is a pole at the origin. Slope becomes 0 dB, meaning that there is a 0 at 0.4, and there is a pole at 10. There is one more pole at 50. We wrote this. And then to know the magnitude of k, let us try to identify the magnitude and the corresponding frequency and write the terms which are contributing at that frequency. At frequency of 0.4, only k and s are contributing, so we wrote this. Then we found the value of k as 400. So then we wrote all the equations that are contributing to omega gc. Since omega gc comes after all the cutoff frequencies, so naturally all the terms have to be included here. So we actually wrote the magnitude equation in terms of dB, the absolute value. Then since we have to find omega gc for a asymptotic thing, we are now considering an approximate value. Of course, when I say approximate, asymptotic and actual value, there is a 3 dB difference at cutoff frequency. So as we discussed in the earlier videos of the Bode plot, maybe in the first Bode plot 1 video, I said that the actual plot, suppose if you take only the first order pole, suppose if the first order pole goes like this, suppose if this is some magnitude, if you write the actual plot slightly deviates like this. It deviates like this. It is perfectly matching with the asymptotic at low frequencies. It is perfectly matching with the asymptotic at higher frequencies. But at cutoff frequency, it will be 3 dB difference from the actual to asymptotic. So these things can be considered by, of course, this will be considered in the asymptotic plot by neglecting that 1 in your magnitude equation. So upon doing this, you got it as 707. Okay, now we shall see this now. So now we have been asked to find again the transfer function, and there are two omega gc's, one here, one here. So let us try to write the transfer function. Gfs into hfs is equal to, we have a k value. Can you see that since the slope is positive, so there is a 0 at the origin. And now see, is the slope again becoming 0 dB? From plus 20 it has become 0 dB, meaning that there is a pole. Where is the pole now? The pole is at 4. So shall I write it as s by 4 now? This is s by 4. Then what's happening at 10? At 10 the slope is again increasing to plus 20 per decade. So there is a 0 at 10. So shall I write it as 1 plus s by 10? Then at an unknown frequency, the slope is again becoming 0. From plus 20 it is becoming 0. So let me write it as for the time being x. So now is it not 1 s by x, because this is slope is again reducing from plus 20 to 0, and then from 40 the slope is becoming minus 40 dB per decade, meaning the slope changes from 0 dB per decade to minus 40 dB per decade, meaning that there are two repeating poles at 40. So I can write it as 1 plus s by 40 whole square. Because why it is whole square is why it is 2 poles means because slope is going from 0 to minus 40 immediately. In the previous case it was minus 20 to minus 40. A change of slope is hardly 20 dB, which is due to this. Now there is a pole at x, and at 40 the slope changes from 0 to minus 40, so there is a repeating pole at 40. Now before we proceed, we need to find out this x as well as k before we find out omega gc1, gc2. Now if you carefully observe the magnitudes, can you see here it is 18 dB, can you see here it is 24 dB here. So now since it is 24 dB, how much is the change in magnitude here? The change in magnitude is 6 dB. 6 dB. Now since the slope is plus 20 dB per decade, we know that plus 20 dB per decade is equal to plus 6 dB per octave. So decade means the frequency has to increase by 10 times. Here the frequency has to increase by 2 times. So it has to be increased by 2 times. Now since the magnitude is increasing by 6 dB, this frequency would have increased by 2 times. So what is 2 times of 10? It is naturally 20. So this x is now 20. X is now 20. Correct? So how we got this as 20 is because here the magnitude, there is an increase of 6 dB. So naturally the frequency has to go by 2 times the 10. So 2 times of 10 is 20. So now we are done with the transfer function. Now we need to find the value of k. How do you find the value of k? So at 4 radian per second, I know what is the magnitude, but I don't know what is the magnitude. Okay, I don't know what is omega gc also. So now, so shall I write 18 is equal to 20 log k plus 20 log omega. Shall I write that omega is equal to 4? I will calculate for k now. I will calculate for k. So what I'll do, I will simply make 18 alpha equals 20 log alpha a, this is an unknown parameter, plus 20 log 4. Shift calculate. I'll get the value of k directly. Now k is 1.98. K value is 1.98. Done. So we are done with the value of k. Next we are supposed to find what is omega gc1 and omega gc2. So at omega gc1, what all okay, now of course, as we did in the previous case, at 4 radian per second the terms contributing are this and this only. So after 4 this will contribute, but at 4 it's only these two parameters. So that's why we took 18 dB and equated to only the magnitudes corresponding to k and s. So this is for k, this is for s. Okay, now this is 20. So how do you find omega gc? To find omega gc1, you consider all the terms that are there contributing at this point. At this point the terms contributing are k and s only. So shall I now equate that magnitude to 0? 20 log of 1.98, because we already found the value of k as 1.98, plus 20 log of omega gc, because I want to find omega gc. So these two terms, that is s and 1.98, will give a magnitude of 0 at omega equal to omega gc. So let me just find out that. So what I'll do is 0 alpha equals 20 log of 1.98 plus 20 log of alpha a, shift calculate. Now this will give you omega gc 1. It is 0.5. Of course, correct. So we have equated this to, okay, 0 is equal to 20 log of 1.98 plus 20 log of alpha a. Fine. So this is omega gc1. So, okay, now this is omega gc1 is 0.5 radian per second. Correct. How to actually make out asymptotical? Of course, even without doing this, can we actually find out? Can you see, this is 4, this is 18 dB. Can you see you are supposed to come 3 octaves back? So what is 3 octaves back? So what is first octave of this? Half of this is 2, another half of this is 1, another half of this is 0.5. So other way of finding it is, of course here it is coincidentally happening, since it is 18 dB, come down by 3 octaves, you will reach omega gc. So when you're going by 1 octave back, it is 2 times less, that is 4 by 2 is 1, and then 1 more octave, again 2 times less, okay, 2 times 2 by 2 is 1, and then 1 more octave back is 1 by 2 is 0.5. So which we got it as this. So since this 18 dB is equal to 3 octaves, I have to come 3 times 2, I have to come back. So twice, okay, 4 by 2 once, this is 1 octave, then it is 2 by 2 is another octave, and 1 by, of course this happens to be 2, this happens to be 1, then 1 by 2 is 0.5. You actually came 3 octaves back to reach omega gc, because this is 18 dB. So by some coincidence it has happened. So to find omega gc2, what you have to do, you have to consider all the equations and don't consider 1 in the magnitude equation, and get the value of omega gc2. So I will not calculate. So just find out this omega gc2. So write the equation similar to this, then discard this 1 and then take out that square root and square. So you will end up with the equation, equate it to 0, you will get what is omega gc2. Okay, this has given you some conceptual understanding of finding the transfer function of a system if the magnitude asymptotic plot is given. Thank you.